This is the continuity equation for holes which we have already derived in the last lecture. Obviously, it is going to be very difficult to solve a problem of continuity equation if we have to calculate all the terms on the right hand side. But for making questions easier, few terms on the right hand side of the equation are ignored depending upon the situations provided in the question. For example, assume that in the question it says that the electric field inside the semiconductor is uniform, which means that the derivative of electric field with respect to x will be 0. Therefore, we can ignore this particular term. Similarly, if it is said in the question that the concentration gradient inside the semiconductor is constant, then we can ignore these two terms as the derivative of hole concentration with respect to x will be equal to 0. If it is said that the generation rate and recombination rate does not vary significantly than their values at thermal equilibrium, and since at thermal equilibrium generation rate is equal to recombination rate, therefore we can cancel out these two terms. Now we are going to discuss a very special case in which we are going to assume that the current is strictly due to diffusion. Therefore, drift current density is equal to 0, which further says that electric field inside a semiconductor is 0. Also, we know that current density due to holes is equal to diffusion current density plus drift current density. Since drift current density is 0, therefore we can write current density due to holes is equal to diffusion current density, and the diffusion current density is equal to minus Q into diffusion constant of hole multiplied by gradient of hole concentration. The actual formula includes a gradient, but we usually assume that the hole concentration is variable with respect to x direction only and is constant with y and z axis. Also, we will assume that the generation rate is negligible compared to particle flux density of holes. So, we will get the modified continuity equation to be like this. Now, we are going to assume a very important and very commonly used assumption, which is steady state carrier injection. Under steady state carrier injection, we assume that we are somehow able to inject excess carriers at one end of the semiconductor, which will increase its concentration at one end, and these excess holes will try to move in the region of the semiconductor where the concentration is less, which will eventually lead to diffusion current. The concentration profile for hole concentration under steady state carrier injection is shown here, where P0 represents thermal equilibrium hole concentration and delta P is the change in the concentration at the surface where the excess holes are being injected. We can write hole concentration is equal to P0 plus del P, where del P is actually a function of x. Differentiation of hole concentration with respect to x will give only differentiation of delta P with respect to x. As P0 is a constant, the differentiation will be 0. Now, if we apply the steady state carrier injection in the modified continuity equation which we got earlier, then we will get del P divided by del T comes out to be 0 because we have assumed steady state injection, meaning that the rate of injection of excess holes is constant with time such that the hole concentration in the semiconductor remains constant, giving us the differentiation of hole with respect to time to be 0. Now we put the value of this equation in this equation. This is a very simple differential equation which after solving we will get the value of del p to be in the form like this. You can see clearly from the concentration profile of hole concentration that as we move towards right side of the semiconductor, the concentration of hole decreases. Therefore, we have to cancel this term. As for higher values of x, this term will keep on increasing. Therefore, we have del px to be equal to, it is also provided that at x is equal to 0, change in hole concentration is equal to del p. And if we put x is equal to 0 in the equation we just got, then we will get the value of a to be equal to delta p. So we have the function del px to be equal to delta p into exponential of minus x divided by under root of diffusion constant of hole multiplied by average carrier lifetime of hole. This question should come in your mind that where are these holes actually going? These holes, when going towards the other end where the concentration of holes is less, they will actually recombine, decreasing its concentration. This particular term under root dp into tau pt is referred to as diffusion length of hole, which is defined as the average distance a hole diffuses before recombining. By doing the same analysis for free electrons, we will get under root diffusion constant for free electron multiplied by average carrier lifetime for electron to be equal to diffusion length of electron. These things are commonly used in questions, especially the steady state carrier injection. Before I end this lecture, I want to clarify few points which confuses a lot of students. We have two terms, low level injection and high level injection, which are described after comparing the excess carrier concentration with majority carrier concentration. Similarly, we have degenerate and non-degenerate semiconductors, which are based on the comparison of doping concentration with effective density of states in energy bands. If you are reading books, then you have gone through different average career lifetimes, and if you are not clear about the difference, then it may be possible that you may absorb wrong concepts like we have tau p, tau n, tau pt, tau nt, tau pe, and tau ne. Here, tau n and tau p are the average carrier lifetime of electron and hole at thermal equilibrium. Also, we know that for any semiconductor in equilibrium, which is direct band-to-band type semiconductor, then the recombination rate of free electron is equal to recombination rate of hole, which will give us eventually n naught upon tau n equal to p naught upon tau p, where n naught and p naught are the thermal equilibrium concentrations of free electron and hole. If we assume that we have a direct p-type semiconductor kept at thermal equilibrium, then we will have n naught upon tau n equal to p naught upon tau p. But since the semiconductor is p-type, therefore p naught will be greater than n naught. And to make the equation valid, we will get the tau p to be greater than tau n, which will give us the statement that majority carrier lifetime is greater than the minority carrier lifetime. You observe that tau n and tau p are the average carrier lifetime for different carriers which can be defined for same type of semiconductor. However, tau ne is defined only for p-type semiconductor, where the suffix Ne denotes that the magnetic area is free electron. Therefore, tau Ne is defined as the average carrier lifetime of excess magnetic carriers. But for direct band-to-band type semiconductor, recombination rate of free electron is equal to recombination rate of hole, which will equal to excess carrier concentration divided by tau Ne. Similarly, tau Pe is defined for n-type semiconductor. Tau Pt and tau Nt are the average carrier lifetime, which includes the effect of excess carriers and thermal equilibrium concentration. These two parameters can be defined for different charge carriers for the same semiconductor. There is no need to learn the notations for different carrier lifetimes, as in different books they may be represented by different notations. My only point is that you should be cautious while reading books and writing notes regarding average career lifetime. And also, I have provided my own notes in video's description from which you can take help if you are writing short notes.